Morning, everyone. So we're going to finish off our nuclear energy section here in taking a look at the other type of nuclear reaction, which is going to be fusion. Up to this point here, we've been studying fission. Basically, all our power plants that are in existence today all use fission. Fission is that word here, breaking up. It involves taking heavier species here, and by breaking them up into smaller daughter isotopes, we see that they actually slowly climb this binding energy curve here. As they get higher and higher and more stability as a nucleus, any extra energy, that mass defect is converted into energy, and we can actually harness that for useful nuclear power. For today, we're actually looking at the opposite side here. For a fusion reaction, we're going to take relatively light nuclei. So we're on the left-hand side of this diagram here. You see that in this case here, the average binding energy actually increases quite dramatically. So that sort of gives us an indication that the mass defect, if you can harness this energy here, you should be able to get a lot of energy gluing these atoms together. There is a downside, however, that these reactions, as we're going to see, typically take really, really intense temperatures, really needs things to be kept in a plasma state here. So again, this is theoretically, this is a good idea, but we still have yet to be able to design something on the Earth that actually uses fusion. But here's the sort of idea anyways here. Fusion is this idea of taking this light nuclei, we're going to glue them and actually piece them together. And by joining them together, they also approach and they get closer and closer to the most stable iron-56. And then we can hopefully in the future be able to harness this energy for nuclear power. So whether it be fission or fusion, both of them end up releasing energy. That's why they are a good energy source. Let's have a look at nuclear fusion now. So fusion reactions are promising. However, the fuel itself, they're promising here because the fuel is inexpensive. We're going to find that you can use everyday materials like water if you can manage to harness it. It's also very abundant. It's also very plentiful where you actually need it. It actually generates no radioactive waste as well. So if you're looking at the slide, you're like, great, right? This is all the best case scenario, right? The fuel is cheap. I have lots of it. There's no waste considerations here. This one here is sometimes considered as the holy grail, right? It's like, if I could harness this energy, if I could utilize it, it should be the best source of energy. It's going to way outcompete any fossil fuels I can burn with the added benefit of it having no waste being produced. Unfortunately, however, the only place that we see so far that we know of that actually undergoes fusion is actually fusion in stars. So in stars here, there's a nice composition picture of what makes up a typical star here. You'll notice majority of a star here is actually hydrogen. Hydrogen can be in multiple different isotopes. It could be deuterium, it could be tritium, some of it's helium, some trace elements of other sources as well. But in this case here in stars, because the star itself is very, very hot, part of the thing that makes the star being able to self-sustain and give off so much energy is the star is actually able to actually fuse hydrogen nuclei together. There's our key word. We're taking light nuclei and we're gluing them together to form things that are heavier. And in this case here, it produces massive amounts of energy in the form of light and heat that we need on our planet. So when we look at the slide here, how do we know what stars are made up of? If you imagine or think back to chapter 2 last year, we talked about here we can point our spectroscopes here at different stars. We can see the absorption spectra or emission spectra that comes off of stars. Essentially, every element has distinct energy gaps, distinct energy sizes. So especially when electrons are excited, they're going to absorb certain unique energies for that element. They're going to also release back that energy in terms of emission spectra. We did a lab on that one there. We can use these absorption spectra or even emission spectra to analyze the composition. So in chapter 3, we had talked about here, there's a very unique amount of energy that we need to absorb to match up with the energy spacings. Nobody has the time to actually send in exactly that energy. So what we do instead is we send in the entire Roy G. Biv. We send in, here's all the energies that you might need. If the energy perfectly corresponds to the size of an energy gap, you notice that the electron has been promoted. It's taken away that color. It dances around for a little while here at a higher shell, and then eventually when it relaxes back downwards, it ends up emitting this energy again, and you notice the energy here that's released is exactly the negative or exactly the same energies as have been absorbed in the first cases. Make sure you're able to explain why it gets closer together at the high frequency end. It has to do with the energy shells converging, so just have another look at that there. And we can actually utilize these absorption spectra here. This is the spectra absorption or emission for hydrogen. Let's compare that with helium here. helium, you'll notice here, has also bands. If I send in the whole Roy-G bit, it also takes away some colors here. When those electrons end up falling downwards, it ends up emitting off color as well. And depending on sort of what emitted spectra, because these lights here are hitting our spectroscopes here, we can not only figure out what elements are present. This is actually the way they discovered helium back then, but they can also discover the proportions as well. So depending on the intensity of light, that might have to do with which transitions are more common, but it could also be a proportional factor to how much of that particular chemical that I actually have. So again, fusion would be a nice model if we can somehow harness it in the future, but so far we're only able to do it in the solar system, where it's already really hot, where things can be kept at a plasma, and that can be a self-sustaining source to provide the sun its fuel. We're going to look at that in a little more detail in the textbook here. Just before we do that, especially when we're dealing with radioactivity, we always need to consider the waste that we're producing. Fusion would actually generate no waste, which is awesome. However, unfortunately for us, a lot of the radioactive isotopes and the waste that we produce, they may actually have very long or short half-lives. Make sure you know this definition for half-life here. We saw it last year. It's the time it takes for half of the numbers of the sample to decay. Now, in terms of decay, it doesn't necessarily mean disappear, right? Sometimes it just converts into another element. You could also qualify that as the radioactive activity. So the fissile, the fissionable kind of type, that activity has decreased 50%. The time needed for that is also called half-life. Half was just convenient for us. We're going to see in the math of this lesson here, we can actually use decay constant instead. It is an exponential decay. Nuclear decay is a random event, so although you can't pinpoint exactly which given atom is going to be the next one that decays, we know that sort of based on my initial sample, I can wait long enough for 50% to decay. When I have half the amount of sample in the same half-life, in the same amount of time, if I wait a second unit of that time, I end up having 25% left. So it's always exponential. Theoretically, it never drops to zero. However, sometimes it gets so minimal that we just basically lose sight of it. Let's have another look at our types of radioactivity. So mainly we talked about alpha, beta, gamma. It's in that order in terms of intensity and penetration power as well. Make sure you know which particle is which. So an alpha particle is a helium nucleus, so just the 2 protons and 2 neutrons. A beta particle is just an electron, but we saw last year this electron is actually coming from the core when a neutron actually converts itself into becoming a proton. Gamma radiation, although the most intense, it is just pure energy. No daughter isotopes take off matter. So in this case here, your species before would just go from an excited state to an unexcited state. So looking at these radiation types here, again, we are steadily stronger as I work down this slide here. And alpha radiation, this is what Rutherford used for his gold foil experiment. This one here can be easily stopped by even a thin piece of paper, doesn't even take much air, right? It's the lowest intensity radiation. A beta particle here on average is about 100 times more penetrating than alpha. You might need a couple meters of air, but depending on different materials, in this case here they're saying aluminum here, it only takes 1 millimeter to actually absorb and actually stop the beta particle. This is not talking about reflecting the beta particles back. This is actually talking about getting rid of the intensity. So basically it's being absorbed away. Gamma radiations are another 100 times more penetrating. In this case here, more penetrating than beta particle. We need some heavy duty sort of lead sources or meters and meters of concrete to actually sort of safely store the energy inside. So as we look at waste in general here, we do want to take a look at storage and disposal. So depending on the particular isotope that we're producing, depending on how much of it, depending on which radiation, alpha, beta, gamma, as well as its half-life, it's going to be considerations that I need to factor in when I'm thinking about disposal. We can categorize our waste into 2 different categories. One is called low-level waste here. In fact, 90% of the waste that's on the Earth is actually low-level waste. Only contains 1% of the total reactivity. So imagine there's lots of quantity of this. We're going to see some examples of this one here. Some sources of this one here that emit low energy alpha and beta particles. Sources are, let's say you were wearing a lab coat, let's say you were wearing gloves and whatnot. You had encountered trace amounts of radioactive material. Now every time you wear a new lab coat, get some new gloves or so, a lot of it is in this low-level waste category. It only contains the least energetic radiation, those low-energy alpha, beta particles, low intensity. So I have huge quantities of it because every time I work with it, I need a new pair of gloves, the idea, but it contains very small fraction of the total radioactivity. Depending on the radiation level here, you might be able to store it on site, right? Because it's such low intensity anyways. You might be able to incinerate it until they get rid of it, or you may be burrowing in shallow pits. Now, what we're more concerned about here is the high-level waste that some of these nuclear power plants actually generate here. For high-level waste, just looking at the numbers here, in fact, high-level waste, it's a very small fraction of the waste on Earth. A lot of it, like we mentioned, were from disposed lab coats, gloves, your protective gear, things like that. But what's going to happen here is a very small quantity of it actually contains most of the total radioactivity intensity. In this case here, the most common source would be, let's say I really do have a nuclear power plant. We had talked about in yesterday's lesson, we needed control rods and we needed moderators to sort of steady the number of neutrons. I don't want it cycling out of control. Once I sort of run out of that sort of radioactive carbon, radioactive graphite rods, things like that, what do I do with that? I don't have huge quantities of it. I don't have many control rods. However, the intensity of these control rods actually contain most of the total radioactivity. Storage and disposal is very problematic. Currently, the most common practice is a guy called vitrification. And in this case here, basically I take that small amounts of really high intense radiation, I fuse it into glass, I store it into cement and whatnot. And what I do is I just do a really deep burial. I hopefully bury it in a place that should be geologically stable so that it's not prone to earthquakes, things like that. So I need to worry about it. But really, because these guys have half-lives on the order of maybe millions of years, you can't store it on site a million years and then dispose of it then. The hope is just, okay, I'm going to store it in really deep caverns here, and I can just keep it there for millennia. Hopefully it gets undisturbed, and basically it'll slowly wait out its half-life. So not the best scenario, I know, but that's what we have so far. Let's switch over to our textbook notes and let's have another look. Okay, so continuing to look at our textbook section on this fusion. Again, the keyword here is we're going to take light atoms. Fusion involves joining them together and forming slightly heavier nuclei. We have upwards of making iron-56. In this case here, because the daughter isotopes here themselves are going to be more stable. Remember, going up on this chart here actually means more stable. As they get more stable, any extra energy gets radiated away. So remember, both fission and fusion, they end up producing daughter isotopes that are more stable, and both of them provide a possible energy source. All of our power plants up to this point have been fission reactions because they don't need the really intense temperatures that we're going to see in this section here. Fusion, we only have a model of it so far for stars. We'll start with that, and then we'll talk about some current technologies trying to start at harnessing fusion with an economical way on the Earth, but never been done so far. So let's just skip down here. We had skipped over this section. This bottom part here, this part here is taking a look at fusion. Let's step through some of the details here, especially when you're looking at stars. All stars, hot objects, they give off electromagnetic radiation at different regions. How much radiation and where the peak actually occurs, what the color of the star is, actually depends on the temperature. The hotter the star is, the more radiation there is, typically at a short wavelength. The sun, for us, relatively looks yellow. So if you imagine, let's say this is the emission spectra, let's plot wavelength. Let's have the 400 side as the purple side and the 700 side on this side. Let's plot the intensity that we're getting from the sun. What we're going to have is, if this is the emission spectra, we're going to actually have this one here have a peak intensity somewhere within, this is the yellow region, which is why it looks to us yellow. But because it does actually give off entire range, it's not that it doesn't give off other colors, it just gives off yellow best more than the other colors. And other stars here might have different temperatures. This curve here might end up pushing over a little bit here. If you want to look in more detail, you can look up something called the Boltzmann intensity distribution. What I want to introduce to you here is this one here only tracks the sun's surface temperature. So you can imagine our sun here. We know the sun in general is hot, but what's happening here is we're actually looking at just the gases on the outermost layer. It's those parts there that are actually giving off the yellow color light that we see. It's possible that our sun itself is actually much hotter inside. When the light or energy came from there, that part there may actually be absorbed by almost like there's no atmosphere, but almost like the surrounding gases, sometimes those surrounding gases can actually absorb some of this radiation, impacting how much energy they actually leave. So all we can sort of conclude here is at least the outer temperature is about 5700 based on the yellow color that we're seeing, but we're imagining that the inside of the sun is actually even hotter than that. They're going to go through a little bit of more detail here in terms of doing the fusion reaction. What I'm trying to do things are like taking hydrogens, right? It could be deuterium, it could be tritium. I gave you this formula in yesterday's lesson here. We can end up fusing together to form helium, and then we end up releasing off some number of neutrons, things like that. So that's a fusion reaction. We're joining things together. And actually just goes through a little bit more detail of why is that hard to do on the Earth. So the practical difficulties here on the Earth here is we have insufficient energy to make it profitable. It's not impossible for you to make a plasma, but you need to imagine, well, where am I going to store that plasma? How much am I paying to actually keep things so hot at such high pressures? How can I work with it safely? Those are all sort of practical issues. Why do we need such hot temperatures like the sun easily has? The hot temperatures are needed to have sufficient kinetic energy that we can actually overcome the natural repulsion. Now, obviously, when I form helium here, I have, let's say, 2 protons. Those protons here are still repelling. Those are still going to be a kq cubed r squared, right? We know Coulomb formula from last year. But what we're doing here is we're actually, the reason why fusion normally doesn't happen is hydrogen would have a proton. Let's say this tritium, slightly heavier form of hydrogen, also has a proton here. Not only is there repulsion trying to keep these two things apart here, these protons, they hate each other. They still hate each other as helium, but there is going to be some added repulsion to glue these two things together. And we need those hot temperatures in forming a plasma state. It's such a high energy state that these isolated atoms and ions that weren't together before, they are able to overcome the mutual repulsion. They're able to fuse it into different nuclei. And basically, yes, even though there is still going to be repulsion, but I'm going to be able to pay enough so that there's enough strong nuclear force to actually keep the atom together. You're going to need really, really hot temperatures. We typically need a plasma state for this. Just a weird comment here. When we actually define energy, especially for charges, we define it when things are at infinity. So charges at infinity, we define that to be 0. So therefore, whenever charges are present, whether it's an attractive or repulsive force here, all these forces are quoted as negative numbers, but we just want to measure how close to 0 I'm getting. 0 is sort of the highest energy case. I just call that 0, and everything else has negative values. So for example, if this, let's say it's a positive repulsion here, these guys here, potential energy speaking, they might have a repulsion of, making up numbers here, maybe they have a repulsion of negative 100. Totally making up that number there. When they're closer, we know closer means they repel more. Maybe they have a energy of negative 10. Right? So that number is closer to 0. They're all negatives, but we're looking at the closer to negative you are. This one here has relatively higher energy. We'll come back to that when we look at batteries in a little more detail. So we do need these really intense temperatures, this plasma state, to actually safely work with it. These are theoretical models that people are working on. So scientists are trying to somehow confine this plasma. Yes, they still need to pay a lot for the really hot temperatures, things like that. What we're going to do is we're going to inject hydrogen into what's called a tokamak, which is a donut-shaped container. The tokamak here is known to have really strong magnetic and electric fields. Basically, we use electric fields to accelerate the positive ions. We speed them up enough so that they can gain that enough kinetic energy and hopefully overcome that mutual repulsion. And then what we have is we have super cold magnetic fields here. We talked about supercooling in yesterday's lesson. That could be leading to disastrous contact for plutonium reactors, things like that. But the reason why we need supercooling here is to generate strong enough magnetic fields so that we hopefully can maintain a plasma, right? It's a hot, intense state here, gaseous, things like that. But we hopefully have enough magnetic fields that whatever walls of the container I have, the plasma doesn't actually touch the walls itself. Then we don't need to actually worry about it melting the surface or whatnot. But for that, we need really, really strong magnetic fields. So in that case there, we typically use liquid metals for coolants here. Again, the same safety precaution as we did last time. So somehow utilizing strong magnetic electric fields here, we generate that plasma, and we somehow need to engineer it in such a way that the plasma actually doesn't melt the surfaces that it's in contact with. Sort of that same idea here, magnetic confinement here. This is using inertial confinement. So this one here is using higher pressure conditions. Again, the emphasis here, the reason why it's our holy grail is none of this has been successful yet, but this is what they're trying. What they're doing here is they're taking little pellets filled with deuterium and tritium here. This time, instead of using temperature or electric fields to actually speed things up, we're actually sending in high energy rays, and hopefully these high energy rays can provide the energy that it needs to overcome that repulsion and end up gluing these atoms together here. So this photon bombardment hopefully squeezes things together. We again need liquid metals to do some cooling. Again, not yet successful, but just different designs to how we may be able to do this in the future. Now here's the advantage. Here's the good thing about fusion reactors if we can harness it. 1 gram of hydrogen, right, not a whole lot, is able to generate enough energy as burning 1,000 kilograms. That's actually 1 ton of coal. So in this case here, we talked about, well, coal is a non-renewable resource, right? This one here had to be formed over millions and millions of years. If I can harness even burning just the odd gram, it's abundant. Hydrogen is everywhere. We can also see here, well, hydrogen can be in the form of water, right? Water is H2O like this. Whenever we have H2O, it could be just our regular old most stable form. It could be the deuterium form. Water is really abundant. So I'm not having to do any really massive transport, massive storing. I'm not going to get a lot of waste because when I burn, we're going to see hydrogen fuel cells later on. The only byproduct itself is water. Maybe the odd hydrogen, maybe the odd oxygen. So I don't have to worry about sort of the wastage problem as well. So it's less dangerous, even if the radioactive byproducts here do have half-lives, they steadily are going to be a little bit less than what it was previous. So that's sort of the fusion model. Let's just flip over to the last side here and talking about waste. So on the last side, after we skip over the fission stuff, nuclear reactors tend to form byproducts. These are the current ones here. You can make a note to yourself here. This is fission, because all we've been able to harness so far is fission. They unfortunately end up producing things that are really hard to dispose of. We need to worry about the radioactivity, right? We need to worry about the half-life, how long it takes to actually drop off. We talked about qualifying the 2 different types of waste. So they're either high-level or low-level waste here. Make a note to yourself, high-level waste here is going to be low quantity. So I don't have a lot of it. But if I have a fuel rod that's used up and I need to replace it, what do I do with that spent fuel rod? When I use it in industry or military, really high activity, they typically have really long half-lives. We mentioned, again, the only solution we've had so far, I might try to absorb some of the neutrons and whatnot, but we had that word here, vitrification. Basically, I try to bury it really deep in a geologically stable area and hopefully let it wait out its half-life. In fact, most of the waste products that we generate, again, in a fission reaction here, we have high quantities of low-level waste. This one here would be when we do research, when we're working in the hospital, things like that. These ones here typically have low activity. They decay enough, so sometimes we just we put it in cooling ponds so that the heat exchange is sort of managed. We can even store it on site until it's fallen a couple half-lives here, and then we end up just dumping it into the sea here. We don't need to have a really deep burial for it. So depending on the level of waste, depending on the half-life of it, we want to get a sense of what we're going to do with it afterwards. So the last part of this lesson here, I just want to show you some of the math of this half-life. So in this case here, the overall, let's start here. Although we cannot predict, so you can make a note here, radiation is a random event, so we cannot predict which atom decays when, right? It's random. However, because I know radiation is just sort of this probability, if I have a bulk sample, if I have many atoms, although I can't predict which particular atom is going to be the next one to decay, I know that steadily some are going to decay, and if I watch the rate at which the overall collection, the bulk sample decays, we talked about half-life previous, again, make sure you know the definition of this one here. Half-life is the time needed to drop, the concentration of the activity to decay away. Again, technically the matter might still be there, but at least not in the radioactive form. Some half-lives are on the order. Here's that uranium-238. That was the non-fissionable one that we saw yesterday. This takes 1 billion years. approximating the Earth's age so far. So if I had 100% uranium-238 at the beginning of our universe, the age of the Earth right now, it would have dropped only 50%. Right? That still may contain way too much radiation to be safely dealt with. Whereas I have polonium here, it's a fraction of a second. So you see every element has a different stability, has a different half-life. So being given the half-life, that's going to decide for me what I do with it in trying to manage that waste. We did an example of carbon-14 dating last year. Basically, carbon-14 dating, carbon-14 actually undergoes beta decay into nitrogen, and it takes a half-life. That half-life is actually going to be a constant. We're going to see that in terms of the rate order stuff that we did earlier in this course here. That constant here is actually independent of your starting amounts. So your calculus here, it says your decay rate, how quickly I have a sample, I have chemical A at my initial time here. The decay rate actually depends on your starting concentration. When your starting concentration was high, the rate of it's high. As the concentration steadily drops, the decay rate is actually dropping as well. Because the rate constant, this really is that K constant we did from our reaction kinetics here. Because this K constant here and the concentration is just to the order 1, we can actually qualify this one here as a first order rate constant. So it's not second order, it's not squared or cubed or anything like that. It's always going to be first order. What they did here is this is the main equation we're working with. So half-life here, basically the rate depends on your starting concentration. It also doesn't change with temperature. That also makes it a little bit different from the K constant we've seen earlier. If I take an integration of this, if I find what function actually follows this behavior, I can actually get these sort of logarithms, right? I'm going to get an exponent come out of it because when I take a derivative, I end up getting the function back. And basically just a little bit of math here. I'm going to take the logarithm of a at time t. I have the decay constant. We're going to see that in our math later on, plus ln of a. I'm going to bring the ln a term over. When you do subtraction of logarithms, it becomes a quotient here, or you can write it here. The amount that's remaining, careful, sometimes they try to trick you and they try to be like, how much decays? Let's say 40% decays. Let's write this in words here. If 40% decays, I don't want you to put 0.4 here. I want you to put 60% left. So put 60% for AT. We're going to see when the time, this time here is called the elapsed time. This is the actual time that you're actually waiting. When the time is actually equivalent to half-life, we're going to see a slight simplification for this formula. The amount has exactly dropped by half. So if this AT here is half of what it was initially, the AO sort of cancel out. We get log of half. I don't necessarily like this fraction here, so I'm going to pull out a -1. So that pulls out another negative, and we end up getting this formula here. Ln 2 is a relationship between this new lambda. The lambda is now going to be called the decay constant. I'll show you an example with this one here. And the half-life. So you can still do your calculations with half-life just like we did previous. I'll show you a derivation of that, getting from that formula to this new formula here. But once we have both, I'll walk you through an example or two. So let's just finish off this lesson here with a little bit of math here. Let's start off with the formula in our data booklet. This is one we did just plain old half-life. So I have nt is equal to n naught. Half-life had dropped by 50% every time. We had t over k. And again, just to qualify these terms here, nt is the amount at time t. That's the final amount. N naught is the amount initially at t equals 0. The t is the actual time you waited. I mentioned this k here we're going to use as half-life. So what I'm going to do here is I'm going to show you a quick derivation. How do we get from that one that was specific to it has to be half-life, it has to be 50, 50, 50. How can we actually reframe it in terms of a decay constant and actually utilize these decay constant functions a little more? So here's what we're going to do. I'm going to bring the n naught over. So nt over n naught, we've done that before, 0.5 t over k. I'm going to take the natural logarithm of both sides. So natural log nt over n naught. That's going to equal to the natural log 0.5 t over k. That natural logarithm here allows me to bring down the t over k. So let's factor that down here. And I'm just going to write this half here as 1 over 2. That's going to become important later on. So we basically have recovered most of our formula. I have the log AT over AO. If you didn't match it up here, so far my right-hand side is now going to look like t over k. And then we have a ln half like that. Right, so and I have basically my formula here. I don't quite have my negative yet. I don't quite have just t by itself. What I'm going to do is this is 2 to the -1. I'm going to flip this fraction and I'm going to pull out a negative. So I'm going to get a negative t over k ln 2, and now I have an exact match to the one that we had earlier. Ln AT over A naught is negative lambda and t. Aside from the negative and aside from the t, this part here should be your decay constant. So that's a new term here. Sometimes they ask you in this section, calculate the decay constant. Decay constant, they're using lambda here, and lambda is going to be ln 2 over k. Or you can rearrange that there, and you can say your decay constant times k is equal to ln 2. That one there is also on your formula sheet. So I just want to show you this new derivation that they showed you in the textbook. It's basically a more generic form. It actually frames it in terms of this decay constant as opposed to half-life, where it always needs to be 50%. So let's try out a quick question or two here. Let's say I have the following problem. Initially, my amount, starting concentration 1.400 times 10 to the negative 6 mole per dm cube. The final amount NT is 1.365 times 10 to the negative 6. Just looking at those numbers here, I definitely haven't waited a full half-life yet. If I had a half-life, it would be like 0.7, but it's only dropped by a little bit. They tell me that this takes 2 hours of time. The question here is just find the half-life. You can totally do it using the formula we did earlier. You can totally do NT N naught 0.5 T over K like you did last year, but using the lens of this decay constant, I'm going to, instead of doing the half-life formula, I'm going to use this new formula here, the newly derived form, a little bit more generic, ln of AT over A naught is equal to negative my decay constant times the time. So let's just punch in the values that I have here. The ln of T, 1.365 times 10 to the negative 6 all over 1.400 times 10 to the negative 6. This is supposedly your new decay constant. That took 2 hours, so keep track of your unit on time. I'm going to just crunch that through there, double check my numbers, make sure you put your brackets in. I'm getting on the left hand side here negative 0.0253. That's negative your decay constant times 2 there. I'm going to divide the negative 2 over, and I now have the decay constant. Sometimes they just ask you, calculate decay constant. That's how you do it. My decay constant is 0.127. Right. The units of this one here, because I know out of the logarithm comes out unitless here, this one here is multiplied by time, so I know this one here actually has to be seconds to the minus 1. Right. But that there is a decay constant. We're going to, again, that's your, so if I have rate is equal to K times your starting concentration, basically this one here is your decay constant. It's a first order decay constant. And it's sort of more generic than just using half-life. Not fully done then you go to your formula sheet and says, well, the decay constant and half-life have this relationship. I can just rearrange for K then. K is ln 2 over this decay constant. So in this case here, sorry, I just realized, yes, it does need to be time to the minus 1, but because they give you time in hours, this time the decay constant is quoted as hours to the minus 1. And that way, when I take ln 2, I divide it by this 0.0127 hours to the minus 1. Ln 2 divided by this answer here gives me a half-life of some 55 hours. All right. So again, nothing wrong with the half-life formula that you used before. I just wanted to show you, just because we've done all that first order kinetic stuff here in chapter 6 here, this formula here is now a little bit more general than the half-life. The half-life one always needs half, 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 right? Just to show you another example why this one here may be an advantage, this generic formula here. Let's say I have 226 radium. This one here has a half-life, so that's going to be a K value. Has a half-life of 1620 years, so long, long half-life. What they're interested in here is calculate the decay constant, lambda, and the percentage that remains after 100 years. Always do a mental check for yourself here. If it's taking 1,000 years for it to decay even by half, I've only waited 100 years, so I'm expecting a lot of it to remain. So in this case here, first thing I would do, because they already give me half-life, let's find the decay constant. If lambda k equals ln 2, let's figure out just what lambda is. Lambda is ln 2 divided by k. K in this case here was 1620. It's in years, so ln 2 divided by 1620 gives me here a really small decay constant, 4.3 times 10 to the negative 4. This one here is going to be years to the minus 1 because, again, it's in years just like earlier. And now that we have this one here in years, I don't need to use half for a half-life and figure out how many actual half-lives have passed by. I can go straight to our formula. This is the generic expression. We saw that it was essentially the same formula as we had derived for a half-life. I have that expression here. I'm going to take exponents of both sides. So natural logarithm here is e to the negative. And now I can figure out, well, if I want to find out the percent remaining, this term here is already the percent remaining. And therefore, I can go, what is e to the negative? The decay constant, the first order rate constant that doesn't depend on temperature, multiply, I've waited 100 years. You punch that through there. E to the, make sure you have your brackets, negative 4.3 e negative 4, give or take a little bit of rounding, I'm getting 0.958. So this tells me here 95.8% remains. It's a little bit hard to do sig figs through a calculation, so usually in a question they'll say state it to the nearest year, state it to the nearest percent, and that's how you do your rounding. They may ask you how much has decayed. If I still have some 96%, you can then say, well, 4.2% has decayed. Right? So on your worksheet, there's a few more practice questions for half-life, and that sort of finishes off our study for nuclear energy. Take a big scale comparison versus the fossil fuel energy sources and the nuclear energy sources that we did over the last couple lessons or so. Think about some advantages and disadvantages of either, and then as we step through the next couple lessons, we'll introduce solar energy and other electrical energy forms as well. All right? If you have any questions, just let me know. Thanks, guys. Take care.